Hello, I'm back for more online material for relativity. This is intended to be a revision lecture for students who are going to take the PHY 350B paper, which contains a single compulsory relativity question. And to help you with this, I recently sent you and also put on the MOL site a mock exam question with the same mark distribution and weighting as you will see on the exam. That is a total of 12 marks for one question. So this is a spoiler warning. I recommend that all of you attempt the question without watching this lecture before watching it, because what I'll do now is show you how it's done, and that's just because it's more effective, far more effective, to revise for yourself and study for yourself and work for yourself than it is to learn other people's solutions. Rote learning of other people's solutions is not an effective way of learning. Fail. Okay, so what we have here is a particle decaying into two photons. And the particle I've given a mass symbol m sub a. I've not told you what that mass is because I'm the sort of guy that likes people not to use their calculators, so I'm not going to tell you the number. I'm just going to assert there's a particle that decays into two photons. And one of the photons, I tell you, is emitted in the direction of increasing x. So if we draw an x-axis under here, then the direction of emission of one of your photons is that way. And then by conservation of momentum, because the initial particle is at rest, the second photon, which we'll call gamma 2, goes that way. So drawing that diagram is something that pretty much everybody should do for the exam. After all, the diagram indicates that you have a clear understanding of the physics, which is that we're in the centre of mass frame, the particle which is decaying is at rest, so there's no momentum initially, and therefore when the two photons are emitted, to conserve momentum, the sum of their momentum must be 0, so that momentum of gamma 1 has to equal minus the momentum of gamma 2, and they're both vectors. But in this case the motion is along the x-axis, which means that py equals pz equals 0. Neither photon has a component of its momentum in the y or z directions, and px1 equals minus px2. In other words, the momentum of the photon 1 is pointed that way, the momentum of photon 2 is in the opposite direction, and the magnitudes of their momenta are the same. Okay? So that's part of the answer to part A, which is what are the momentum and energy of the two photons. The other part of the answer is actually to figure out the magnitude in terms of the rest mass of the decaying particle. Well, by conservation of energy, we know that E gamma 1 plus E gamma 2 has to equal the total energy of the particle that's decaying, which is ma times c squared. But we also know that the energy of each photon equals the magnitude of its momentum times c, and since the magnitude of the momenta of the two photons are equal, that means that E gamma 1 equals E gamma 2, which equals, well, we'll just call it E. Right? And that implies in turn that E gamma 1 plus E gamma 2 is just 2E, and that has to be equal to ma c squared, so that E of each photon is ma c squared upon 2. Okay? So the answer to part A is that E gamma 1 equals E gamma 2 equals ma c squared upon 2. Now for the momentum, we know that E equals Cp, which means that P gamma 1, which is the one going to the right, has to equal plus mac upon 2, because to get from E to P I divide by C, and P gamma 2 equals minus mac upon 2. And that critical minus sign will is probably the bit that most students would tend to miss out. That's the mistake I would most often see in this part of the problem. Okay, so now I'll clean the board and we'll go on to the next piece of this problem, which is part B. Do that quickly with the video on. You always have to excuse me for doing silly things with the video on, like cleaning the board, and if you'll notice the phone went just now. Fortunately I did at least ignore it. So there's very little editing of these videos. If there was, I wouldn't have time to make them. Right, so part B. So now we've got a frame, a reference frame that's moving in the direction of increasing x with a velocity v equals beta c with respect to the lab frame. So in the lab, that's the rest frame of the decaying particle, right? And that's the direction of increasing x. We've got a frame which is at rest with respect to the lab, which I'll just call the lab frame. And there's also another frame which is moving that way, velocity v equals beta c, with respect to the lab, and we'll call that the primed frame. I hope you're all happy from the lectures with the concept of frames of reference. A frame of reference is basically, you can think of it as a coordinate grid which moves at a constant velocity with respect to the lab or with respect to another observer, and none of these frames are accelerating. They're all moving at a constant velocity, and you can tell you're moving at a constant velocity because there are no forces, but you don't feel any g-forces. G-forces are forces due to acceleration. Okay, so in special relativity we think we know what constant velocity means. It means there are no forces. Okay, so I remind you of Lorentz transformations on energy and momentum. So at the beginning of the course, in the first year, we discussed the Lorentz transformations on x and ct, and it turns out that Lorentz transformations on pc and e are exactly of the same form as the Lorentz transformations on x and ct. And so by analogy, we can write down that the energy in the primed frame, E primed, equals gamma times the energy in the unprimed frame minus beta pc. And that's analogous with ct primed equals gamma ct minus beta x. That's what you can notice the form of this equation is basically the same as the form of that equation. So the transformations on E prime, it's the same form as the transformation of ct prime. And there's also another one, which I'll remind you of, so that momentum in the case where the boost is in the x direction, so in other words the prime frame is moving in the direction of increasing x with respect to the lab frame, pc primed equals gamma pc minus beta e. So those are the Lorentz transformations. I recommend that you make yourself comfortable with them in your exam preparation, not just relying on the fact that the Lorentz transformations for x and ct are written on the front of the exam paper. You should know the Lorentz transformations in energy and momentum, because they may well come in handy, and if you try and write them down, deducing them from the ones on the exam paper, you may get factors of c in the wrong place and end up coming to grief. Okay, so in this case, which one of these are we going to use? Well, the question is, for what value of beta, in other words, how fast does the prime frame have to be moving, does this photon, the one that's going in the direction of increasing x, gamma 1, does this photon end up having an energy which is E over 2? So as you know, its energy in the lab frame, we did this in the last part, the energy of the gamma is ma c squared over 2. And so what we want is beta such that E primed equals half E. Okay, so how are we going to do that? Well, of course, you can see it's going to work if we have an observer who's running along in the primed frame. To that observer, the photon is going to have a lower energy because of the Doppler shift. So it doesn't appear to slow down. To all observers, it moves at the speed of light because it's a photon. But it's going to have its energy reduced because its wavelength is going to increase because the observer is receding from the source of emission of the photon. That is the decaying particle A. So let's see if we can write down some equations. Start with the Lorentz transformation. Write down E primed equals E upon 2 and substitute that in. So E upon 2 equals gamma times E minus beta. Now beta is just V over C. PC for a photon equals E. So instead of writing PC, I'm simply going to write E here. So that means that E upon 2 equals gamma, factor out the E, times 1 minus beta. Okay, so that equation is interesting because the E's cancel. So you end up with an equation for gamma and beta, and that equation should allow you to solve for beta. So let's see how that works. So let's erase everything except that equation that we derived. 1/2 equals gamma times 1 minus beta. Now here we can take advantage of some things we know about gamma and beta. Gamma equals 1 over the square root of 1 minus beta squared. But that equals 1 over the square root of 1 minus beta times 1 plus beta. Okay? So what we have here is that 1 minus beta, that's this 1 minus beta, over the square root of 1 minus beta times 1 plus beta equals 1/2. Alright? But that means that 1 minus beta squared over 1 minus beta times 1 plus beta equals 1/4. The reason I've done this is because now we can cancel one of the factors of 1 minus beta in the numerator with a factor of 1 minus beta in the denominator. Now why do you care about that? Well, the reason you care is because that cancellation stops the equation being quadratic in beta. So now there's only going to be one solution for beta instead of 2, which is a good thing. It's going to make the equation easier to solve. So take the 1 plus beta underneath and bring it up to the other side. We get 1 minus beta equals 1/4 times 1 plus beta, or 1 minus beta equals 1/4 plus beta over 4, or 3/4 equals 5/4 beta. What I've done there is move the beta over this side, move the quarter over this side, and then that means that beta equals 3/4 times 5 over 4 times 4/5, sorry. So that beta equals 3/5, or the velocity of the primed frame with respect to lab is 3/5 of c. And that was the answer I was looking for here. So a key point is, I've stayed in algebra all the way to the end. Right at the end, it turned out I hardly need any algebra. In fact, beta equals 3/5 is a perfectly acceptable answer. If you multiply by 3 times 10 to the 8 and express v in meters, I'll give you the marks too, but it doesn't make much difference to me. Okay, in the next segment, we'll go ahead and figure out the other photon's energy in this frame, and then we'll have a look at what happens when you add those two energies up.